Hello everyone. In this video, we will see our in this video, we will see the next problem, which is subtree of another tree. This is a easy problem, but it is like medium problem, but it is marked as easy. So, anyways, we will go to the problem description and two methods. We will see the two solutions. So the given roots of two binary trees, root and subroot, and return true if there is a subtree of root with same structure and node value of the subroot, and false otherwise. A subtree of a binary. So what we have to do is, if the given parent tree contains the subtree, then we have to return true, or else we have to return false. So in this case, the subtree is present here, as you can see here. And also, a subtree of a binary tree is a tree that consists of node in a tree, and all these nodes are descendants. And here it is given the definition of subtree, and the tree could itself be considered as subtree of itself. So what it means is, for example, if we were given here subtree as same tree as this tree, then in that case also it should return true, because it is saying here, the tree could also be considered as a subtree of itself. So the tree itself is also a subtree. And you can see in one condition here is, you can see in example 2, you may be thinking this will return true, because here we have let me just here we have the subtree, but no, in this case it will return false, because the subtree should be like only tree will be called subtree only if it is present at the end. So that is what it was given in description, as you can see here, the definition of subtree. A subtree of a binary tree A subtree of a binary tree is a tree that consists of a node in tree and all of these nodes descendants. So that is what it is saying. So it should be at the end. So let me just clear this, and let me go to the constraints. So the constraints are the number of nodes in root tree is in range this, and the number of nodes in the subtree is in this range. And as you can see, the parent node has many nodes than the trail the subtree. And root value will be these are the given like parent node values and the child node values. So let's go to the first solution. So these are the two methods, and these are both recursive methods. So this is the first method, is like little bit seems hard, which I have done, but the second method is very seems it says very easy, like I have seen this in taken this from the lead code solutions. So this seems like easy method. So yeah, we will go through each method. Yeah, so let's go through the second method first. So we will discuss, so here I have taken the our example, which is 3 4 5, this parent node and parent tree and subtree. So initially, in method 2, what we are doing is, uh, initially in method 2 we get root, Here I'm giving the addresses like 101, 102, 103, 104, 105 for easy purpose. And for Subtree also I have given the addresses like you can see here 202, excuse me, 201, 202, 203. And initially we get initially for tree we here you can see initially we get here is subtree. Here I am considering as I sub. And initially we get and also is same as I same. So initially we get 101 and 201. So we here we get that 101, 101 and 201. Initially we check if 101 is if root is none, it is not, so we'll go this condition becomes false, and we go the here which is we come here and we check. Now we pass for each same method we pass again 101 and 201. So here when it comes 101 and 201 comes here to this method, and initially these two condition becomes false. And here this condition also becomes false because these two are not equal. As you can see 101 the value at 101 and 201 are not equal. 3 is not equal to 4, so that is the reason here this will becomes for this will become actually yeah, this condition becomes true, so this will return false. So that's how we get false here. And then later that false we get here. And we will since this condition is false, so we will not go inside if condition, and we will call the is subtree is same is subtree, like it we call itself with root left. So that is the root left is 102, so that is the reason 102, and we are passing 201 again, which is subroot which is 201 address. And it will go inside this is same, and these two three condition, in this case the three conditions becomes false because initially root is not none, and subroot is not none, so this is false. And here nothing is false, like any one is also not false, so this is false. And values are same, as you can see 4 is equal to 4, and like value at 102 address and 201 are same, so that is the reason this becomes false, and it will come here. And now recursively it will call the same method with root left and subroot left, which is root left is 103 and subroot left is 202, so that is what here it is calling here. And then next it will again come here, and again these three conditions becomes false. And again it will recursively call root left and root left, which is left of this is none and left of this is none, so it is calling none and none. So in this case these conditions become true because both are none, so it will return true. So that is the reason here we are getting true returned here. And then we get true here, so we got true here. And then we will then call right side method, recursive method. So that is what here we are doing, right side we are calling, which is right side of 102, which is 104, and right side of 201 is 203. So that is what here we are calling 104 and 203. And then again when we recursively come here, these three conditions become false because these are not none, any two any one node is not none, and also these two values are same, 2 is equal to 2, so that is the reason this condition also becomes false, and it will come here again. And here it will again call root of left, so left of it will call left. So 1 or 2 left is none and 2 left is none, so it will call none and none, and it will return true because if none if we here these conditions become true, so it will return true. And here we get true value, and again it will call right side one, right side of 2, and right side of 104 and 203 is none. So again it will call yeah, yes, is same of none and none. So again this will go inside if this if condition, and it will return true. So again like and forgot to mention here also, after calling the left method it will call right method. So we get true. So now we got true here and true, so it will return true. So the true will come to is subtree, and here this is r. So if any one if the first condition is true, then it will not go to it will not check this condition at all. So this will directly return true. So so that's how here it will return true. So this is how it will work, this method will work. And as you can see, the subtree is getting compared at each step. So what's happening is here is subtree is comparing with each element in worst case it will compare with each node in a root tree. And if here as you can see here it matched, and when it matched it will compare with all the nodes in subgroup. So and if anywhere it becomes false, again it will come to this method. So here if instead of 1 if we would have uh, uh, here if instead of 1 if we would have 5, then this condition would have become false, and then we would have again started comparing what 202 201 and 103. So that is the reason it will compare if m elements are there in root tree and n elements are there in subroot, then the time complexity is m would be m into n, because of we are comparing each node in subroot with each node in root in worst case. So this is the time complexity of worst case. And the space complexity is order of m, because let's assume it is recursively calling this method. And so for recursion we need a stack. So internally it uses stack. So recursion tree height would be maximum height would be m, because if this tree is left screwed or right screwed, in that case uh, uh, recursively it will call m times the total number of nodes in root node, which is m. So that is the reason here space complexity is m. So this is our solution one, solution method 2. So this is actually a very good method. So and also a standard method. Let's see our first method, which seems little bit harder, but like that both time complexity and space complexities are same for this method as well. Yeah, let's go through the solution. Yeah, so here initially we get and also for this also we can see this graph, this diagram, so you will get a good idea. Initially we get root and subroot, which is again address of root is 101 and 20 this subroot is 201. So we get 101 and 201. And here in we are calling is same, and we are passing root and subroot. So that is what here we are doing. We are calling is same and one passing 102 201, and also we are passing 201 two times. So the reason is, I'll explain while going through solution. So like in recursion, this value gets changed, but this will not changed. And whenever some condition becomes false, we will replace this with this our root. So in recursion, whenever there is a condition becomes false, we want root of this subroot. So that is the reason we are maintaining the that root recursively in this variable. So yeah, so here we get 101 and 201 201 at for at this method. And initially these two conditions becomes false, so we will not go inside those conditions. And then this condition becomes false because 3 is not equal to 4, so it will come here. And uh, subroot current subroot, this is subroot current, and subroot current is not equal to subroot current, then it will go inside this if condition. This is false because we already have 201 201 same, so we will come here. And we will check we will pass root left because these both are not equal, so we will be comparing this with again this. So we will come here, we pass left of 101 which is 102, and these both are will be passing subroots. So we will pass here 101 left is 102 201 201. So this becomes recursively, when we call this method recursively, this condition becomes true in this case because 4 is equal to 4. So value at 102 is equal to value at 201. So that is the reason it will go inside this if condition. And recursively here it will call root left uh, source current subroot current left. So left of root is 103 and its root left is 201 so it here it is calling 103 202, and this will remain same 201. And again these two are same 1 and 1, so again it will recursively call left of this and left of this, which is none and none. So at this place at this time this condition becomes true, so that is the reason it will return true. So here we get again true, and then we call right side because this condition became true, and we'll be calling the right side one. So again this condition like right side of 1 is none, right side of this 2 1 is none, so none and none, again this will return true. So this condition has become true. Again this whole condition this left it became true. And now it will check for right side. So again right side we will be checking right side of 102 is 104, and right side of 201 is 203. So to 104 203, so these are both are equal, 2 is equal to 2, value at 104 and value at 202 are same. So that is the reason it will again recursively call left method which is none and none. This will return true again, and again it will call right side and it will return true. So again we get true, so at that time this second condition becomes true. First condition has become true and second condition became true, so that is the reason it will return true back. Here it will return true, and when it return true it will come here, we got here true. Just like the previous method, here we are using r. So this condition became, if this condition became true, then we will not going to check this condition. So here this will return true. This is how this go method is going to work. So whenever there is a r, then it will first check the first condition. If first condition is true, then it will not going to check the second condition at all. Only it will check the second condition only if the first condition is false. So if there is a and, then if first conditions become true, then it will definitely going to it will check second condition as well. And if first condition is false, then it will not check the second condition, because true false is false. So it will not check the second condition when first condition is false. So this is how the first method will work. And like I was saying, why this the second root node is useful. mm, uh, for example, this will be useful uh, if we see the example too, or here I can tell you. So assume in this case, like let's it's better to take the one example. Yeah, so in this case, initially it will compare this value and this value. This becomes false, so it will start again from here at this place, and this becomes true, and it will compare this again, this node with this node. This becomes true, and it will compare left of this node, and it becomes true. Left of this node becomes true, come back, and it will compare this element and this element. So it is true again, and it will again compare the left of this and left of this, which is false, uh, which, which is false. So if we would have not written this, in this case it will go inside this condition. You can see at this place this is false, so this condition becomes false here. So, and also this condition becomes true here, because current subroot is not equal to subroot. So we will go inside root, and we will not call root left, we'll be just calling root, and we will reset this subroot. So we will again pass subroot. So that's how what we are doing is here uh, we are, once this condition becomes false, we again started checking 4 2 4 2. If this condition was not there, then it would have returned a false from here itself, and it would have gone back. So we should check the left of 2 as well. For example, assume if there was something here this way, 4 1 and 2, then in this case it is not checking the right of or left of 2, it is just returning false. But there is a sub sub subroot in our tree, so this should return true. So that is the reason this condition, in this case this condition becomes true, and it will again start from this node, instead of just returning like false here. So this is how it's going to work. So yeah, these are our two solution, and here also we are comparing each here we comparing each node in subroot tree with each node in root tree. So that is the reason the time complexity is order of m into n, and the space complexity is order of m, because recursively we are calling. And in a case where a tree is left screwed or right screwed, we recursively call the each node, and the height of the tree in a recursive tree would be order of m, like the total number of nodes in root tree. So that is the reason the space complexity is order of m. Yeah, this is it, and I have shared this solution in here in lead code solution. So I'll share the link of this solution as well as the image that we have discussed in the description of this video. uh, that's it. Thank you for watching.